Xu, and this is my demonstration of Module 3. Today's agenda is pretty simple. It's all about MRC and ANOVA. I'm going to introduce multiple regression and correlation first. Then I will introduce a little bit more about analysis of variance. The purpose of MRC is to measure the relationship between one single outcome and several predictors. There are several predictors because social science interacts with the real world. In real world situations can be very complicated. It's extremely rare to see one single predictor predicts one outcome. Usually several predictors go together to predict the outcome. And when I think about the real purpose of MRC, the first word coming to my mind actually is the causal effect relationship, to measure the causal effect relationship. From my understanding and from my undergrad research method education, it's really reluctant for me to say that, because they kind of advocate to express about correlation instead of causal relationship, because it sounds more scientific. But I believe this approach receives criticism from Professor Gary King. He kind of advocates the expression of causal relationship, causal effect in regression analysis. He believes that the nature of regression analysis is conditional probability distribution, not variable X predicts variable Y. So it's very it's okay to express a causal relationship in regression analysis. Here is the simple formula for multiple regression, where Y represents the outcome and beta naught or B naught. I'm going to pronounce it B naught here. B naught is the intercept. It is the best guess when there are no predictors. And x1, x2, and xk, they are all predictors, obviously. And b1, b2, bk, they are all weight assigned to the predictors. And as epsilon, is residuals or errors. Why we can add up so many variables, so many predictors in this equation, I will explain later in the next slide. Here are some underlying assumptions about multiple regression, and the first one is linearity. As I mentioned before, we can add as many predictors as we want in our model, because the underlying assumptions that is the nature of linear regression is it's called linearity. It allows the additivity of the relationship between dependent and independent variables. And also the multiple regression also assumes that all the residuals are normally distributed and there are no or little correlations between predictors. And also there are little or no correlations between residuals or zeros. And at last, there's constant variance among errors. Well, here is my cursory handwriting of my own self-made bivariate MRC, and I will just skip it and come directly into MRC with software. Well, I use the Module 3 data, and I kind of regard Y as the outcome variables, X as the predictor variables, and F as the group vectors, which I'm going to mention it later in the ANOVA. And well, here I use Y1 as my outcome, X1 and X2 as my predictors, and here's a beautiful chart made by SPSS. When we first look at the R square, which had a fancy name of coefficient of determination, it actually measures how close the data are to fit the regression line. And as if it is perfect, if it is a perfect no variation fitting, it should be 1. It's kind of like a percent. And here it's relatively low. It's only 0.3. And we also want to look at the Durbin-Watson as the the Durbin-Watson test to see the figure there is 0.211. Actually, Durbin-Watson measures the autocorrelation. Autocorrelation is kind of the correlation between residuals or errors. Remember what I mentioned in the underlying assumptions? The residuals should be independent from each other. So Durbin-Watson 2 in Durbin-Watson test, 2 actually is pretty good because 2 equals to 0 correlation, and the scale or the range of Durbin-Watson scale is from 0 to 4. 2 in the middle means good, means satisfying, and we shouldn't be worried about so much. Well, let's see the coefficients chart. We want to first definitely look at the multicollinearity of our predictors. Well, we see the BIF, the variance inflation factor, which is pretty small. It's not problematic. It's only have problematic when it is greater than 5, and it's super problematic when it reaches 10. And we see the t-test, and we see the significant level, and we see that x1 is not definitely not x1 is definitely is a predictor of y1, but whereas x2 is not. Well, in order to test for the homoscedasticity of the errors, I prefer to use constant variance of errors. We use the PP plot, and here is you can see the line. It is not perfect, but it's still satisfying because it didn't vary too much from the black line. And we also want to see the normality of the residuals to see if it is normally distributed. I did the scatter plot to see. I think it's not problematic because it's within the range of +3 to -3. But in order to double check, I didn't put the histogram here, but I did in my SPSS, and it confirmed that it is a normal distribution curve. Well, outliers are super influential to multiple regression results. We must consider the effect of outliers when we do the diagnostics. So here, Cook's distance measures the outlier effect. So we look at it, and to see the maximum here is 1.053. There are different theories about the numbers, like the level should be that which the outlier should be eliminated. Some theory just said if it exceeds 1, it should be eliminated or negated. And some theories suggested it should be the 4 divided by n. If it exceeds that number, it should be avoided. But under those, even for those series together, under our circumstances, 1.053 definitely exceeds their levels, so its outlier should be avoided. But we also want to see how it might influences graphically or visually in graph to see the outlier effect. And we can look at the plot there. It's upper there, and it's an outlier. And sometimes, most scientists agree that outliers should be avoided, but not according to Cortina. Cortina kind of said that it's temptation to avoid outliers which affect your grade because to avoid outlier to affect your results. But outliers can be categorized into 2 different categories, and it should have different impacts on the data. And there are variance outliers and covariance outliers. The covariance outliers directly impact the covariance, and the variance outliers directly impact the variance. So you should be considered about the effect when you kind of want to avoid all the outliers, kind of to seek for the category to see if this really impacts it. The comparison with MRC, they kind of both have they're both output contain an ANOVA table, but for ANOVA it kind of tested for the mean difference between subject groups, whereas MRC kind of tested to the causal effect, yeah, according to Gary King. And ANOVA usually using a combination of categorical scales and numerical scales. You know, they kind of tested between groups. Groups have names like genders, something like that. So you should sometimes use the categorical scales, whereas MRC, they all use continuous scales, pure numbers. And for the and they both love variance. Yes, as the beginning of the class, professor told us, variance is the king, but they kind of use variance in different ways. And for ANOVA, they didn't like correlations, whereas in our MRC correlations are everywhere, and especially the kind of residuals. And ANOVA is kind of usually implemented in, or it is widely used in design experiment. For instance, it's like the control group experiment, double-blind experiment, whereas MRC usually used in inferential stats, like how this sample can generalize into can be inferential to the whole population, and they all shared one underlying assumption is the normality. The normality of the data and the variance of the homogeneity. And here is what I did for the ANOVA in SPSS. Y1 is the dependent variable I'm going to talk about. Both F6 and F7, the factors, the group factors I mentioned in early slides, they are independent variables. I'm going to run through it. Well, you can see the results of the table. You can see they are not statistically important because they all exceed 0.05. And in order to double check this, I'm going to run the Levene's test of homogeneity of variances. As you can see, the results here, it's also non-significant, which means it assumes the homogeneity of variance between groups, which also means, in turn, means that there is no significant difference among the groups. And I also want to wrap up with a test of normality for both F7 and F6 to see if they are normally distributed. We use the test of Shapiro-Wilk to see, yeah, all of them are non-significant, which fails to reject the null, which is satisfying, which is a good thing because the null here is they are all normally distributed. So that is what our underlying assumption is. It should be normally distributed, all the data. And now let's check. Let's double check with the histogram. You can see the normal distributed curve. So, and that's all for today's module. Thank you very much.